Okay, recording is started. So good morning, everybody. Welcome back to Math 115. I hope you guys had a nice kind of restful weekend after the exam. So before we start, maybe I'd kind of like to hear from you guys about the exam. How did it go? Any comments, any questions, anything to say at all about the exam? Hard, but you think you did okay. Same deal. Okay. Yeah, so I mean, I think it's not too surprising, hopefully, that I think the unit circle stuff, trigonometry in general is, I think, harder than what we were doing before. The only really kind of tricky thing that we did before we started doing trig was, I think, exponentials and logs were had some challenging material in there. But I think really the main difficulties in this class all kind of come from this trig stuff in the unit circle and all that. Question 3. How do I unraise my hand? I don't actually know the answer to that question. Oh, it's on like the emojis thing. If you click on the emojis, I think that's how you do it. There's like a hand there. There you go. Let me see what question 3 was. I forget. Was that the word problem? Yeah, that was the word problem. The number of bananas sold. Yeah, so basically, a transformation of a trigonometric function. That's a good problem. Yeah, I think that's definitely one of the harder problems. So if that's the one you struggled on, that doesn't surprise me. Question 3 was fun. No, Savannah, I did not post a new homework to be due this Friday. We just didn't have enough new material. I didn't feel like it was would have been that meaningful for me to post anything. So yeah, no homework due this Friday. Captain says, question 3 was fun. I'm glad you found it fun. I think it's kind of enjoyable to do problems like that where it's, there's some kind of meaningful, it's almost like a game, trying to solve those word problems. Okay, well, thank you everybody for your comments on the exam. I haven't started grading them yet. I'm going to try to grade them today and tomorrow. So as usual, I'll just try to make sure I get them back to you guys on like a week-long timeline. So I should definitely have them done by this coming Thursday. So I will grade them all on Notability, and I'll send you guys a PDF of of my comments on your exam, as long as you submitted your exam as a PDF. If not, then you'll have to meet with me during office hours or something to get feedback on your exam. Okay. So let's go ahead and start. This is going to be week 14, which, by the way, is the second to last week, I think, of classes. So we're almost done. So this week and next week, we're basically going to do like a couple sections of chapter 6, and that's about it. So your final exam is going to be on May 4th. So there's a 1 week period in between where you guys have like a dead week where I think instructors are not really supposed to assign anything. And so I won't be doing that, but there will be a review session somewhere in that week. I'll do like a really long one for you guys, and presumably Jamie also has a review session somewhere in there. So just make sure you check the Blackboard for that, because we won't have class for me to be kind of reminding you guys. So I'll communicate with you guys via email or Blackboard. So May 4th is when the final exam is, and it'll have the same structure as usual. I'll give you the exam at like 8 in the morning, and it'll be due at 9 p.m. Only it'll be a little bit longer than the other exams that we've had so far. So it'll be probably closer to 10 problems as opposed to like 6. Okay, so that's that. So this week, what we're going to do is we're going to finish up 5.5, which is like, I mean, we just have a couple examples left that I wanted to do on these trig equations. Okay, and then we're going to start chapter 6. Okay, and chapter 6 is still trigonometry, but chapter 6 moves away a little bit from the unit circle. Okay, so trigonometry is something which can be done really in principle just using triangles, okay? Just using triangles. And so far, that triangle has always been inside of the unit circle. And that's how we've been able to know that the side length of the hypotenuse of our triangle was equal to 1, right? That was how we kind of gamed the system. But we can do trigonometry with triangles, okay, whose side lengths might be different numbers, like the hypotenuse could be 6, and then this would be like, I don't know, 3, and then this would be 36 minus 9 square rooted. Okay, so we can have triangles with all sorts of different side lengths, and we can still do trigonometry by considering things about this angle theta, right? And this might be the type of trigonometry which you first learned if you've learned trigonometry before this class, which is not really required. But if you did learn it in high school, you might have learned about like SOHCAHTOA and how to do opposite over hypotenuse and adjacent over hypotenuse and opposite over adjacent and all of that jazz. So we're going to talk about that stuff, and that's going to be in chapter 6. Okay, but before we do that, let's do these 3 final examples, which I wanted to talk about from 5.5, which I just never got to. Okay, so this first problem here, okay, is a problem where we're given some information about what is sine theta. Okay, what is sine theta? And we're supposed to find cosine of 2 theta, given that information. Okay, so we want cosine of 2 theta, and we know sine of theta. Okay, so sine of theta is like 4 over 5. 4 over 5, so we know we're talking about a point on the unit circle, which is, you know, either up here or over here. Oh yeah, that makes sense. So then we're supposed to find cosine of 2 theta. Okay, well, let me ask you guys, do we have any identities which relate sine theta and cosine of 2 theta. Do we have any identities that relate sine theta and cosine of 2 theta? Here we've got I think a major clue here is going to be these angle measurements. On one of them, we've got an angle measurement of 2 theta, and on the other one, we've got an angle measurement of just theta. Okay, Kumar, I like it. Yeah, we've got a double angle formula. Let me copy in the relevant identities. What do we have? So I think the one that Om Kumar was putting in was this one. Double angle formula. Let's copy it, put it over. I like it. The other interesting one that I think we could use would also be a half angle formula. So I'm going to copy that one too. The reason that the half angle formula came to me first was just because, as I said, these are kind of like the most useful ones for calculus. So these are the ones that I keep memorized. Add a page here. But I think it's always fun when you guys come up with ideas that are different than the ones that I had in mind. So let's go with this one, because this is what was suggested by a student. Okay, so we want to use this. We want to use this identity here, okay? And the nice thing about it is, well, the thing we want to know is nice and squarely on the left-hand side. So the left-hand side is already just what we want to know. And the right-hand side is all stuff that we can find out. Almost. Yes, it is all stuff that we can find out, actually. Okay, because first of all, sine theta is just 4/5. So this is just going to be 4/5 squared. And we actually can find out what cosine squared of x is. Can somebody tell me how we can find out what cosine squared of x is if we know what sine of x is? Oh yeah, 1 minus sine squared would also work. Let's see, was that another double angle formula? It probably is. Oh yeah, that would have worked. We could have just used this one, right? 1 minus 2 sine squared of x would also work, and we could just do 1 minus 2 times 4/5 squared, and that would get us the answer. So that would be a really quick way of doing it. But let's say that you only remember this one on the exam. Well, you could still use this one as long as you remember the following. We have that sine of theta and cosine squared theta satisfy the Pythagorean theorem. So we also know that cosine squared x plus sine squared x is equal to 1. So cosine squared x is equal to 1 minus sine squared x. Aha, okay. I see. You were not suggesting another double angle for me. You were suggesting to use the Pythagorean theorem to find out what cosine squared x is. Yes. Okay, so then this would be cosine squared x would be equal to 1 minus 4/5 squared. So then cosine 2x would be equal to, well, we're just going to plug that in for cosine squared x. We get 1 minus 4/5 squared minus 4/5 squared is equal to 1 minus 2 times 4/5 squared, which is equal to like 1 minus let's see, this would be 16 over 25, so 32 over 25. 25 minus 32 is negative 7 over 25. So that's how we could take this route. Okay. The one that occurred to me was to try using one of the half angle formulas, because this right here, this cosine 2x is what I want. So I just start with the half angle formula and then I rearrange. So I'm going to multiply by 2. So I get 2 sine squared x is equal to 1 minus cosine of 2x. So I add cosine x, 2x to both sides. We get cosine 2x plus 2 sine squared x equals 1. So then cosine of 2x would be equal to 1 minus 2 sine squared of x, which is exactly that formula that we had, one of the double angle formulas. But I can never remember the double angle formulas, but I always remember this one because it's very useful. And most of the other ones can be derived from it, as I've just shown. So then this is how I would do it, and then you again plug in 1 minus 4/5, 2 times 4/5 squared. Okay, so I think these are both great ways to do this problem. So thanks to all of you guys who suggested ways to proceed with this problem. Any questions about this problem? I think it's a pretty standard application of an identity. Which identity you use kind of just depends on your frame of reference. If you want to call it a half angle or a double angle or power reducing or whatever, just pick one and go with it until you can kind of get what you want. Okay, the first one I think we had to use 2 identities. But the first identity was one of our double angles, and the second identity was just one of our Pythagorean identities, which we kind of can always keep in mind. Okay, so that's a nice problem. You know, it's a problem where we really don't ever get a hands-on idea of what theta actually is. You know, we haven't really been told what the angle is. And so finding cosine of 2 theta, well, we're going to have to rely on the identity because we just don't know what theta is. So that's a clue if you have a problem like this, that you should definitely be approaching this with an identity in mind, because you don't actually know what theta is. And in fact, you can't even really find it out, because if you have 4/5 here, well, you'd have a triangle here whose height is 4/5 and whose radius is 1, and this is not one of our special right triangles. So you wouldn't even be able to find out what theta is without using, say, a calculator and a sine inverse function. And even if you did, you would get some decimal and you'd have to multiply it by 2 and then use a calculator again to find out cosine of 2 theta. And we haven't really talked about how to do any of that. So the way we have to approach a problem like this, where we really don't have our hands on what theta actually is just to use these identities, which relate trigonometric functions of angle measurements, which are twice of the angle measurement for another trigonometric function. Okay, so those identities are, of course, the double angle formulas and the half angle formulas. Okay, so that's a good problem. All right, so now let's try this next one. We're supposed to find x such that tangent of x is equal to -1. So let me draw, and let me not use that color. Let me draw a unit circle. And let me label my quadrants here. And let me ask you guys, in which quadrants do we expect to find x, the angle, such that tangent of x is equal to -1? In which quadrants do we think that's going to happen? Well, Kumar says 2 and 4. And I like that answer. The reason that I like that answer is because we have the old mnemonic device, right? It was all students take calculus, right? ASTC. And ASTC was used to tell us where is the tangent function going to be positive, or where are the trigonometric functions going to be positive. Well, it says all trigonometric functions are positive in the first quadrant. Just sine is positive in the second quadrant. Just tangent is positive in the third quadrant. And just cosine is positive in the fourth quadrant. So we have an angle x, which gives us a value of tangent, which is -1. So our value of tangent is negative, which means that we should not be in the quadrant 3 where tangent is positive, and we should not be in quadrant 1 where all trigonometric functions are positive. So we're going to check for angles x which lie in these two regions such that tangent of x is equal to -1. Okay, tangent of x is equal to -1. So if we have a point on the unit circle, x comma y, let me draw it in. And why don't I'm going to switch this to be theta, because this is just going to be easier if we're talking about theta. Tangent of theta is equal to -1, okay? So we have in here an angle theta. And remember that tangent of theta was defined to be the ratio of the y coordinate of this point to the x coordinate of this point. Okay? We had an angle theta, we check the point on the unit circle, we divide the y by the x, and that is the definition of tangent. So tangent of theta is going to be y divided by x. And we know that this is equal to -1. Now, if I focus in on this equation, I can learn something interesting. If I just multiply both sides by x, then the left-hand side would be y, and the right-hand side would be -x. So what have I found out? I have found out that the point on the unit circle, which is going to satisfy this equation, or the angle on the unit circle, is going to produce the angle measurement, which is going to produce the result tangent of theta is equal to -1 is going to correspond to a point on the unit circle which satisfies the equation y is equal to -x. So I can draw this in onto my graph here. This is just a coordinate plane, and y equals -x is a line with slope -1. And what does it look like? Well, it looks like it goes straight through the origin, out like this, kind of, and also up in this direction. So this is the line y equals x. So I need the angles theta, which are going to point at this point here, which is the point -√2/2, comma √2/2. And at this point down here, which is the point √2/2, comma -√2/2. Well, we have two angles which immediately come to mind. The first one is theta is equal to, well, here's pi/2 and here's pi. So halfway between pi/2 and pi would be 3pi/4. Or theta is equal to what? This would be that plus pi, so 7pi/4. Okay, so we found the two angles which are between 0 and 2 pi, which cause tangent of theta to be equal to -1. Now our question was to find theta such that tangent of theta is equal to -1. We found two angles where it's true. My question to you guys is, are there any other angles, theta, such that tangent of theta is equal to -1, other than the ones that we've already found together? Yeah, exactly. We can add 2 pi n to any of these, or to either of these two angles. Okay, so let me draw in what I mean with this kind of orange color. So this angle theta, which we've drawn in yellow here, is going to point at that point x comma y, and we're going to get tangent of theta is equal to the ratio between square root of 2/2 to negative square root of 2/2, and that's -1. But we could also draw in the angle theta, which starts at the same spot, goes and does a full 360, and then goes the rest of the way also to this thing here. And that angle theta will have a measurement which is, I don't know, like, 2 pi plus 3pi/4. Okay, and that'll have the same terminal side. Okay, these angles are coterminal. So this other angle, theta prime, also satisfies this. So what we can do is we can take 3pi/4 and we can add 2 pi n. We can add 2 pi n. Okay, and likewise for the other one, we can add 2 pi n. And in fact, there's a really much nicer way to write all of this, which would be to say, well, theta is equal to 3pi/4. And to recognize that, well, 7pi/4 is exactly pi away from 3pi/4. So anything of 7pi/4 plus or minus 2 pi n for an integer n is going to be some constant multiple of pi away from any of the other angles. So we can write this as theta is equal to 3pi/4 plus pi n. And this should not be too surprising, considering the fact that we know that tangent of theta is pi periodic, meaning that it takes the same value for any distance angle measurements which are pi units apart from one another. Okay. So that's how we could find an even nicer closed form for this than we had before. Okay, and it's not that surprising if you look at the graph of tangent as well. What does the graph of tangent look like? Well, we have all these asymptotes. And the graph of tangent just looks like, well, it starts at the bottom, goes up to the middle, and then goes up to the top. And then again, it just repeats. Right? This is what the graph of tangent looks like. So this is like saying, well, the height of the function will be 1 at all of these points here, which are exactly pi units apart, right? When will the function value take 1 again? Well, it's a pi periodic function. So pi units away, we'll take that same height again. So that's another way of thinking about this. Okay, any questions about this this problem? This problem was a bit more general. They said find theta such that tan theta is equal to -1. And well, if you want to answer the question in the most complete way as possible, you need to give every single value theta for which this is going to be true. So you can't just say theta is equal to 3 pi over 4 or 7 pi over 4, because there are infinitely many more angles which we could choose, which will also cause this equation to be true. So if we want to express all of them, we say, well, theta is equal to 3 pi over 4 plus pi n, where n is an integer. And then this kind of encapsulates everything. Okay, every angle that could possibly cause this equation to be true. Okay, any questions about this problem? Okay, seems like not. So we'll do this last problem here. It looks like a doozy of a identity verification. Okay, so let's just take in what we have on both sides. Well, the left-hand side, we've got a product a product of sine functions. And then on the right-hand side, we have sine of 2x. Well, this is interesting. Well, let me ask you guys, what do we think about this? Is there any identities which we want to try using to try to solve this verification problem? Does anything stick out to you? maybe this is a trickier problem. Okay, my hint to you guys is to maybe start by, oh, that's an interesting path. Yeah, we have an identity involving sine of pi over 2 minus x. It was the cofunction identity is what we called it. This was equal to cosine of x using the cofunction identity. That's true. And let's see where that gets us. Wow, I think that is a really beautiful way to take this problem. That hadn't even occurred to me. This can be written as sine x times cosine x is now equal to sine of 2x over 2. Yeah, that's a great way to do this. So now we're almost done. What can I do to finish this up? Yeah, we can multiply both sides by 2. If we do that, we get the equation sine of 2x is equal to 2 sine x cosine x. And now I claim we are done. Why are we done? This is a true statement that's underlined in green. It's true because this is one of our double angle formulas. Okay, so this one's known to be true already. Yeah, very good. Okay, yeah, that turned out even better than I could have come up with it. My initial thought was to maybe try using the product to sum identities, and you'd wind up with some stuff where you'd add or subtract these things, and then we might have to use a cofunction identity later on. But yeah, that's really smart to try to use the cofunction identity right away and just focus on that one term on the left-hand side and replace it, because then everything just kind of falls right out. Okay, that's really cool. Nice job. Any questions about this problem? All right. Yeah, pretty standard identity verification here. All we want to do is just rearrange this equation until it looks like something which is obviously true. Now, obvious is sort of a dubious term in mathematics. So when I say that this is, quote, obviously true, I don't really mean that it's obvious per se. I just mean that this is one of our double angle formulas, which we know to be true, and we can check it by going back and looking at the notes. We know that this is true, and if we can recognize that this is one of our double angle formulas, then we are pretty much done. Okay. All right, so that's it for 5.5. So we're done with all of that stuff. So what we're going to move on to now, okay, is what the book calls right triangle trigonometry. Okay, which is just trigonometry involving a right triangle, which is not necessarily inscribed in the unit circle. Okay, so maybe I can explain this a little bit better by adding a page in here. So before, we did trigonometry in the following way. We had a unit circle. And we would put a triangle somewhere inside of it, right? Such as this triangle here, right? And this would be our angle theta, and then we'd put a right triangle here, and we knew that this distance here was 1, okay? And then this distance was y, and this distance x was x, and then what did we do? We said, well, then that sine of theta is just equal to y, and then cosine of theta was just equal to x, right? But if you've ever learned SOHCAHTOA, we know that sine, okay, if we do SOH, it's sine is equal to the opposite side length over the hypotenuse side length, which in our case, the opposite side length is exactly y, and the hypotenuse side length is exactly 1. So y divided by 1 is just y. Okay, but we can extend this framework a little bit by saying, well, now we're not going to necessarily consider a triangle which fits nice and neatly into the unit circle. We're also going to consider the possibility that our triangle looks similar to this one, but it's like much bigger or smaller. What about this triangle? Well, we know something about this triangle as well. We know that this triangle has the same angle theta in this corner, the same angle, right angle here, and the side lengths are going to obey the same basic properties. So if this is C and this is B and this is A, then we know that B over C should be equal to the ratio between Y and 1. The ratio between the side length B and C, so the opposite side and the hypotenuse of this similar triangle, should be the same as the ratio between y and 1 of this triangle. So this is the new way in which we're going to define sine of theta, is it's just going to be a ratio of side lengths. Okay, so that's where we're going with all of this. Okay, so any triangle that we draw is going to be similar to some triangle which is inside the unit circle. So as long as we have a triangle, we can do trigonometry using this basic relationship about similar triangles. Okay, so that's where we're going. Okay, so first of all, we need to define what a right triangle is. And this has sort of been tacitly assumed that everyone knows what we're talking about when we talk about this, but for some reason it's defined here. Okay, so the right triangle is just a triangle which has a right angle inside of it. Another thing that might be a little bit confusing going forward is that some of the triangles which we draw wind up looking a little bit different. Like we'll put the right angle up in the top left or something like this. Okay. And I don't want anyone to be confused by that, because all you have to do is take this thing and like flip it around, and then it'll look like what you want. Okay. You just move it around and it'll look like how you want it to look. Okay. So if they give you a triangle which looks like this, or even one which looks like this, okay, it's no big deal. We can handle that as well in the same way. We just need to remember that when we rotate it like this, well, the C gets moved over here, the B gets moved over here, and then the A is over here now, okay? So we have to just make sure that we rotate the side length with it. Okay, so sometimes they'll give you those funky looking right triangles, but they're still right triangles. Okay, so it just has a right triangle or right angle inside, and one thing that I want to just point out as being new is that the hypotenuse now is not necessarily equal to 1, okay? It could be some other number, okay? So the triangle is not necessarily inside of the unit circle. Okay. So we have one big fact about the right triangles, okay, which is the following. The lengths of the sides of a right triangle obey the Pythagorean theorem. So this little GIF thing here is a way of visualizing why this is true. Well, you take the areas a squared and b squared and sum them up, and they look like the area of the c squared when you kind of expand out this box here. So that's a really cool way of seeing the Pythagorean theorem. Okay, so that's the one thing that's really going to be underlying pretty much everything we do with triangles, is we're always going to be working with right triangles, and these right triangles have side lengths which obey the Pythagorean theorem. So we should never forget that this is also something which we can pull into our work at really any time. Okay, so last thing we'll talk about today is the following. Okay, we call something a Pythagorean triple. Okay, a Pythagorean triple is a collection of 3 numbers, okay, which describe the lengths of a right triangle, and all of these numbers are integers. Okay, for example, the numbers 3, 4, and 5 form a Pythagorean triple. Why? Because I can draw a right triangle. Oops. I can draw a right triangle whose side lengths are 3, 4, and 5, and in fact, these numbers obey the Pythagorean theorem, right? We've got 3 squared plus 4 squared is equal to, oh, I've written it down already. 3 squared plus 4 squared is equal to 9 plus 16 is equal to 25, which is 5 squared, right? So we've got 3 squared plus 4 squared is equal to 5 squared. So if we have 3 integers, okay, so no fractions, no decimals, 3 integers which satisfy this, we call them a Pythagorean triple. Okay, Pythagorean triple. So I think 3, 4, 5 is probably the most famous one, and we call those triangles, quote, 3, 4, 5 triangles. Okay, but there are all sorts of other ones, so I'll give you guys a couple minutes. Try to think of another Pythagorean triple on your own. Okay, so try playing with some numbers and see if you can find some very nice integers like 3, 4, and 5 or some other numbers. Okay, such that when we put them on a triangle, we put them as the side lengths of a triangle. The Pythagorean theorem is satisfied. If you find one, you can put it in the chat. Six, 8, 10. Let's check it. 6, 8, and 10. That would be 36 plus 64. 36 plus 64 unfortunately gets us 110, which is close. Close to 100, but not quite. No cigar. Nearly there, though. There's one that's really close to this. Wait, hang on. 36 plus 64. No, this is 100. What am I talking about? The hell is wrong with me? Yeah, this will work. For sure. Any multiple of 3, 4, 5 will also work. Yeah, so this works. That's good. What am I thinking? Yeah, 6, 8, 10 works. Also, any other multiple, so something like, I don't know, 30, 40, 50. Take a 3, 4, 5 triangle and multiply everything by 2, it'll still work out. There's one other kind of important one, that a lot of people know. It's 5, 12, and 13. All right. So these are Pythagorean triples. Okay, I think I'm over time, so let's stop here for today, and we'll pick this up tomorrow, and we'll talk more about Pythagorean triples, and we'll talk about actual trigonometry. Okay, so thanks everybody. I'll see you guys tomorrow. Office hours start now. If you have questions, feel free to stay after class. I'll be here until 10:30. Yep, you too, Heidi. Thanks.